Okay, this is going to be a tutorial for 3.3.3 trigonometric ratios. But first I want to introduce the reality of trig ratios and the need for them through this example right here. If you take a look at this, the variable is not one of the sides of a right triangle, so we cannot solve for x using the Pythagorean theorem. That's the unfortunate thing when it comes to scenarios like this, because x is an angle. And when we solve for Pythagorean theorem, we use the sides of a right triangle, and it has nothing to do with the angles. But right triangles with the same acute angle measures are all similar because of angle-angle similarity, and therefore they all have the same scale factor. They all use that ratio, and those common ratios that you can use for all right triangles that have the same acute angle measurement, those are stored in your calculator. And they're stored behind three buttons: the sine, the cosine, and the tangent button, abbreviated sin, cos, and tan. These ratios are the ways that you could pick two of the three sides. So I'm just going to kind of run through that with you real quick. So all relative to this angle here, we would call the leg that does not touch x, we call this the opposite leg. The leg that does touch x, that's going to be the adjacent leg. And across from the right angle, the longest side is, and always will be, the hypotenuse. So these three ratios, sine, cosine, and tangent, abbreviated sin, cos, and tan, they are the ways that I could pick two of the three sides of the right triangle. So the ratio sine, and it's going to be the sine of whatever angle we're focused on. So in this case, it's x. So the sine of that x is the ratio of the leg opposite and the leg, and the hypotenuse. So it's the opposite leg compared to the hypotenuse. The cosine of that angle that we're focused on, it uses the ratio of the adjacent leg and the hypotenuse. And then finally, the last remaining pair is the tangent ratio, and it compares the ratio of the opposite leg to the adjacent leg. So how are we going to use this? Well, our calculators, again, have every single one of these three ratios for every single one of the right triangles that we could come up with. They have that. Again, all right triangles with the same acute angles are similar. So they all have the same scale factor. They all have the same ratio. So that means these ratios can help us find out what we're missing because of the similarity of the triangles. All right, so let's try to put a little bit of this into motion for you. You've got to start at the top of your notes, which is a clever way of using and memorizing the three trig ratios that we just introduced: sine, cosine, and tangent. So we have this acronym SOHCAHTOA, and here's how you use it. So S stands for sine, and the two letters following, O and H, are a reminder that that's the two sides that you're using, the opposite and the hypotenuse. So that's the ratio, with the first letter being on top and the second letter being on the bottom. Opposite over hypotenuse for sine. Ca, C-A-H, C for cosine, is equal to the adjacent over the hypotenuse. And the tangent for T is OA, opposite over adjacent. And that's how we're going to use and memorize these ratios. So let me give you a couple examples how we can put this into motion and why it matters and how it's helpful. Okay, so a little bit further down, we've got a few examples that I want to try to work through with you and show you how we can use SOHCAHTOA. And again, keep in mind, we've got SOHCAHTOA here that we can use as a reminder of our three ratios. All right, everything is relative to the one acute angle that you know. So I focus on 32 immediately because when we talk about opposite or adjacent, that's all relative to the angle that we know. So relative to 32, X would be the opposite leg, and across from the right angle, as always, is the hypotenuse. The adjacent leg would be this blank side right here, but because it's blank, I don't know anything about it, which means I'm not going to worry about it. I'm not going to use it to help me solve. So I got to use the information that I've got, which is opposite and hypotenuse. Well, which one of these three ratios uses opposite and hypotenuse? Well, that would be sine. So the sine, abbreviated sin, of the angle that I know, 32, is the opposite leg over the hypotenuse. Setting up that equation is so critical for you because you got to make sure you choose the right, which one of the three ratios that are important. And again, we labeled our parts opposite and hypotenuse relative to the one acute angle that we know, and we made that decision according to our SOHCAHTOA. If we had other parts, then we would use another ratio. Now what I can do is solve, and I want to use my scientific calculator. So at this point, if you'll go ahead and take a second and make sure that your calculator is in degree mode. So you could go to mode and work through that, but make sure you're in degree mode. And then that way, degree like the degrees of our angles, that way we're going to be able to all find the same answers as opposed to them being in another form. Now what you can do is actually get a number to work with for the sine of 32. You look at sine of 32 and it's a little strange, but remember what sine of 32 actually means. It's basically the piece of information that tells your calculator which right triangle you're working with. And what it means is it's a right triangle with a 32-degree angle where the leg across from it and the hypotenuse are the two angles that the two sides that we're interested in. Let me say that one more time. Sine of 32 is what you type into your calculator to tell your calculator which right triangle we're looking at. We're looking at a right triangle with a 32-degree angle, and we're interested in the leg across from 32 and the hypotenuse. So when you go to your calculator and you type in the sine of 32, it's going to give you back what the scale factor is for every single right triangle with a 32-degree angle and the opposite leg and the hypotenuse's ratio. Is going to give you that number. So in your calculator, you type in the sine of 32 and you hit enter, and you should get 0.53 when you round to the nearest hundredth. And that right there is the ratio that the opposite leg and the hypotenuse of every single right triangle with a 32-degree angle has in common. And I can use that 0.53 and help me solve for x. So now I'm just back to a normal algebra equation. How would I get x by itself? I would multiply both sides by 10. And that's going to give me x is equal to 5.3. So now I've just discovered what the length of the opposite leg of a right triangle when I didn't know enough parts to do Pythagorean theorem, which is pretty impressive. Okay, now we're going to focus on another example where the angle's in a different location and I've got different information, but it's okay. I'm going to use SOHCAHTOA to help me figure out which ratio I'm going to use. So focus on the one acute angle that I know, and every angle side location and side label is relative to that angle right there. So according to that 62, the side across from it, the leg across from it, that's the opposite leg. And the leg that touches it, that's the adjacent leg. Now this side right here is the hypotenuse, but it doesn't have any information there, so it's not going to help me. So now I'm looking at my SOHCAHTOA and I'm trying to find which ratio uses both the opposite and the adjacent leg. That's going to be T for tangent. So the tangent of the acute angle 62 is opposite 15 over adjacent x. And so now what I'm going to do is I'm going to use my calculator to figure out what the tangent of 62 is and set that equal to 15 over x and solve. Okay, so in your calculator, the tangent of 62 is 1.88 if you round to 2 decimal places. And now I can solve. If I look at this as a proportion, it might be easier. So you cross multiply in this scenario. 1 times 15 is 15. 1.88 times x is just simply 1.88x. Now to get x by itself, I'll divide both sides by 1.88. These cancel, so x is equal to 15 divided by 1.88, which in my calculator I get 7.978, so that's going to be 7.98, and that is the length of the adjacent leg of a right triangle with a 62-degree angle in it. Now we're going to move to another example where this time we don't know what the acute angle is, and we're going to have to do a little bit of inverses to try to figure that out. We still focus on it as it helps us figure out the labels for all of our parts, but watch how we solve. It'll be slightly different. So relative to this angle, this is our adjacent leg, and as always, across from the right angle, this is the hypotenuse. So I don't know any information about what would be our opposite leg, so I'm not going to even include that. So the ratio that I'm looking for has adjacent and hypotenuse. Well, that's my cosine. So the cosine of the acute angle x is the adjacent leg over the hypotenuse. So the problem right now is that I can't type cosine of x in my calculator and get a number. I don't know how to do that. I want to get x by itself, so I've got to get rid of cosine. Now, cosine is a new mathematical operation, and I've got to figure out a way to undo this new thing. Well, if you look on your calculator, right above the cosine key, you'll see in small letters something that looks like this. Now that's called the inverse cosine. And inverses work against each other and cancel each other out. So if I want to get rid of the cosine and get x by itself, it makes sense to take the inverse of it. But just like any equation, I can't take the inverse cosine of one side without doing it to both. So that means I have to do the inverse cosine of 15 over 17. So what happens to these two inverse operations? Well, they cancel each other out because they're opposites, and now I'm only left with x. And in your calculator, you are left with something that you can type into the calculator. So if you hit second cosine, it'll give you inverse cosine, and then type in this 15 over 17, and that will tell you what x is going to be equal to. So the inverse cosine of 15 over 17 is 28.07. And that's degrees, because what you just discovered is the right triangle with an acute angle whose cosine relationship is 15 over 17. Well, that would have to be a right triangle with an acute angle of 28.07 degrees. That's every single right triangle that has a cosine relationship of 15 over 17. Running out of time, so I'm going to do one more example with you where we don't know the acute angle. I went ahead and I labeled the parts. I've got the opposite leg and the adjacent leg, so the ratio that I'm looking for will end up being tangent. So the tangent of the acute angle, in this case x, is equal to the leg opposite and the leg adjacent. So now I've got to do inverse because I want to get x by itself. So the inverse tangent of both sides is what's going to help me get x by itself. So x is equal to the inverse tangent of 61 over 11. And according to my calculator, that would be 79.78 degrees. So that's the acute angle measurement of a right triangle whose tangent relationship is 61 over 11.